Lab 4 Oscillations. Our problem this week was to see if we could analyze the complex motion of a spring mass system which swings in an arc while oscillating on a spring. By analyzing a video of the spring mass system with Tracker, I collected data which I inputted into a computer simulation I coded using VPython. As a result, I successfully produced a model which gave me findings such as the spring mass system did satisfy the energy principle, and insights into the oscillation periods along the x and y axis. To start, let's go over the main physics principles present in this lab, the first being Newton's second law, or the momentum principle, which I use to update the position and the velocity of the spring mass system. The energy principle also plays a major role in this experiment and states that the total energy equals a change in kinetic energy plus a change in spring potential energy plus a change in gravitational potential energy. Now let's go to Tracker to see the video analysis. The blue vertical line is the calibration stick and measures to be 0.7 meters and spans from the attachment point to the hanging mass. The origin was placed at the attachment point as well. After marking the center of mass frame by frame, I collected the x and y data points in a CSV file, which I imported into my code. Next, I set my initial conditions. Given mass is 0.402 grams, initial position I obtained from Tracker, initial velocity is a zero vector since it's starting from rest, and my start time is at t equals 0, as well as my time step I chose to be a very small number. Other initializations include defining my known gravitational constant. I also had to use some physics intuition to define my spring constant and relaxed length. I used the equation t equals 2 pi the square root of m over k and rearranged it to solve for k, which is my spring constant. The average of 3 oscillation periods, I averaged 3 oscillation periods for my t and arrived at 6.0998 newtons per meter. Since the system starts off in static equilibrium, I can set my forces equal to one another to solve and find for the relaxed length of 0.0541 meters. With these constants in place, I calculate the length of the spring at each time interval. We now turn to the system energies. As stated earlier, we needed to calculate the change in kinetic, change in spring potential, change in gravitational potential as well. Once I define these equations in VPython, I then set them equal to variables that will change in values as the system moves. I still need to calculate the forces on the mass. I define the weight force, or the force of gravity, in the negative y direction. The spring force is Hooke's law, and totaling these two forces gives me my net force, which I use to update the velocity using Newton's second law, which I then use the velocity to update my position. Since the position and length of the spring is changing, I use these lines of code to update the spring with each time step. My changes in all energies also need to be updated with each iteration. We then plot all these changes into a graph. Now let's run the model. The blue ball is our model, and the red is our Tracker data. The black arrow is gravity force and does not change. The blue arrow is our spring force and increases and decreases with each oscillation as the tension in the spring increases and decreases. Finally, the net force is represented by the yellow arrow. As you can see, both balls follow the same path as the time goes. The red ball, or our Tracker data, shows discrepancies. This is due to the drag force catching up to the spring force, or it could be human error in exacting point mass location. Here is a closer look at the graph generated by the model. Blue is our kinetic energy, red is the spring potential, green is the gravitational, and yellow is total energy. I'm going to use this to answer our next question: what does it mean? For your model, is the energy principle satisfied? Looking at this graph, we can see that our system satisfies the energy principle, which states that work done by the surroundings should equal the energy in the system. Because we include everything in our system, the mass, the spring, and the earth, there will be no work done by the surroundings. Our total energy should be 0, which we see is true from the yellow line on the graph, meaning that energy is conserved. Our next what does it mean question asked us to estimate the oscillation periods in the x and y direction. I obtained this data from Tracker and averaged 3 periods along each direction and found the x to be 1.613 seconds and my y oscillation to be 1.267 seconds, the difference being 0.346 seconds. This is because the oscillation in the y direction is based off mass and stiffness, while in the x direction it's based off length and gravity. Ultimately, it takes more time to move one cycle in the x direction than it does in the y direction. Thank you for listening.